In this video, we're going to determine the integrated rate law for a second order reaction and what that implies about the time dependence for the concentration of a given reactant. Okay, so if we have some hypothetical reaction here with some reactant A and B, and we assume that this reaction is second order in A, zero order in B, then we would have that our rate of reaction V of T is equal to rate constant times concentration, molarity of A squared, being second order in A. And according to our previous definitions, this is minus 1 over stoichiometric coefficient of A times the change in its concentration over time, its time derivative of the molarity of A. As in the previous video on first order reactions, we're just going to simplify that this stoichiometric coefficient, we're going to set it equal to 1. Normally that would just get absorbed inside the rate constant, or it would be kept up during the solution, but just one more constant I don't necessarily want to deal with here, so we're going to set it to 1 and just assume it gets absorbed within the rate constant if that coefficient is indeed not 1. Okay, so we want to isolate the things that depend on T and the things that depend on A on each side so we can integrate this equation here, integrate this differential equation. So I'm going to multiply both sides by minus dt over A squared. And when I do that, what I should get is minus k dt equals dA over A squared. Okay, so they're separated, so I can integrate now. So I integrate both sides. I'm integrating from t equals 0 to t equals t. And I'm integrating from the concentration at t equals 0, which we define as A naught, and the concentration at t equals t, which is A of t. Okay, so if we do this integration, then we have integral of dt is t, t minus 0 is t, so we have minus kt for the definite integral on the left, equals. On the right, we have the integral of 1 over x squared dx, which is minus 1 over x. So we have, it's going to be minus 1 over a, and that's going to be evaluated at two different values. It's going to be evaluated at A of t, and it's going to be evaluated at A naught. Okay, you notice that there's a minus sign on both sides, so I'm going to just change that to a plus. So we're going to get kt equals 1 over A of t minus 1 over A naught. All right, and then I'm just going to move the 1 over A naught to the other side, so add 1 over A naught to both sides. We're going to get 1 over the time-dependent concentration of A is equal to 1 over the initial concentration of A plus kt. So this is our final integrated rate law for a second order reaction. Integrated rate law. So we see it's different than the integrated rate law for the first order reaction, which we had in the previous video. So what I've got here is a graph on the right of the concentration of A as a function of time. So concentration graph versus time. And you have three different reactions here which have a different rate constant. All are being second order in A. And if you have the higher rate constant, your initial rate is higher, and then we see it decreases. You know, this behavior is inverse of A, so it's 1 over A, but it's a translated 1 over A, so it doesn't have, the asymptote would be on this side of the axis. So it's kind of asymptotically approaching 0 there, but you notice after a steep initial decay, it starts slowing down a lot because it depends on the concentration of A squared. So as A goes down, this rate of reaction starts going down a lot more because it depends on A squared, and A squared is getting very small very fast. And then if the rate constant isn't as high, it decays more slowly. If the rate constant's even slower, it decays even more slowly. But because of the structure of what I have here, you'll notice that I have a linear equation if I'm talking about graphing the inverse of A. So I have a linear equation y equals mx plus b here. So it's a linear equation if you graph 1 over A versus time. You have your slope is just k, your reaction or your rate constant. So slope equals rate constant if you graph 1 over A versus time. And your intercept there is your inverse of your initial concentration. So for determine if a reaction is second order, you can plot the inverse of the concentration versus time, and if you get a straight line, then your reaction is second order in whatever reactant you're talking about, and your rate constant is determined by the slope of that graph.